Welcome to the 1998 Walter Langbein Lecture. My name's Mary Anderson. I'm from the University of Wisconsin in Madison, and I'm the president of the hydrology section. This is the sixth lecture in our annual series, which is made possible by individual gifts from AGU members to our hydrology section fund. The funds are used to pay the expenses of the speaker and to tape the lecture. The lecture is selected each year by a committee, and this year the committee was chaired by David Freiberg. I'm very pleased to introduce this year's speaker, who is Dr. Mark Meyer, Professor Emeritus of Geological Sciences and Fellow of the Institute of Arctic and Alpine Research at the University of Colorado in Boulder. He is also a Fellow of AGU and a recipient of the prestigious Horton Medal. He's the author of about 200 publications on subjects ranging from glacier dynamics to snow and glacier hydrology, iceberg calving, and global climate change. Mark was drawn into geology through his love of mountain climbing. As a student, he worked on glaciers in Wyoming and Saskatchewan, completing the PhD under Robert Sharp at Caltech. There he says that his most important lesson as a graduate student was learning not to be afraid to question authority. Mark's strong connection with hydrology might be dated from 1956, when Luna Leopold, then chief hydrologist of the Water Resources Division of the USGS, asked him to start a glaciology program. Mark set up an office in Tacoma, Washington, which was to become a kind of school of glaciology. He began the long-term observational program at the South Cascade Glacier, making continuous measurements of runoff, mass balance, climate, and ice flow, and thereby establishing the first complete mass and water balance program for glaciers in North America. Mark was active in the International Hydrological Decade and set up water balance stations on other glaciers as part of that initiative. He has also been involved in remote sensing studies on snow and glaciers and in measuring heat and instability of snow and ice on volcanoes, including Mount St. Helens. He's also been involved in the investigation of calving of great glaciers for the U.S. Coast Guard. He's an advocate for an interdisciplinary approach and has himself successfully bridged the gaps between the disciplines as related to studies of snow and ice. Recently, he became interested in explaining and predicting the role of glaciers in causing sea level rise and in using changes in these ice masses to make inferences about fluctuations in climate. He's developed a global synthesis of the role of small glaciers in producing sea level changes, and it is this work that he will discuss today. Land Ice on Earth, a beginning of a global synthesis. Ladies and gentlemen, Dr. Mark Meyer.
Thank you. Mary, that was a wonderful introduction, and I thank you. It's a very great honor for me to be selected to give this Langbein lecture. I've long considered Walter Langbein as one of the giants of our field. As a graduate student at Caltech, I was already deeply committed to a career as an iceman, but I did take up a little study of drainage basin geometry. I measured lots of area-altitude relations for basins in all kinds of terrain, then normalized the heck out of the data and found some interesting relations, which we would now call stochastic and self-similar, but I didn't know the words then. I was urged to publish, but I first wanted a review by Luna and Walter Langbein. Walter especially was very critical, but his points could not be denied. My paper was never published, but I developed an enormous admiration for Walter Langbein, and now I'm coming back around to such things as stochastics and self-similarity. Luna offered me a job, as Mary said, with the Water Resources Division in 1956, which I readily accepted. Any organization that included such bright scientific leaders as Langbein, Leopold, Metallus, Bredehoft, and others couldn't be all bad. I subsequently enjoyed working with Walter and greatly benefited from his wit and insight. My last contact with him, as you see in this slide, was to present him the International Prize in Hydrology on behalf of the International Association of Hydrological Sciences in 1982. That was a great honor for me at that time, and I am certainly greatly honored for the opportunity to further celebrate his impact on our field today. Now let's turn to the subject of glaciology. Earlier was mentioned South Cascade Glacier. Here it is. But first I must apologize for the title. I am not going to talk about all land ice, and in fact I'm going to ignore most of it. I'm not going to talk about the Greenland and Arctic ice sheets. I will talk about the little glaciers, little as in the state of Massachusetts, or even smaller. These are, however, of great interest to deciphering global patterns of climate change as sources of runoff in many areas, and in the aggregate are far more important in producing the present rise in sea level, unless what Bob Binchadler told us earlier is correct, and maybe they're one of those most important components. This is also a progress report. I will not deliver a signed, sealed, and delivered conclusion at the end, but only show you that we are progressing toward what I think is a great new method. Now, here is the menu. First, glaciers in the Earth's system. That's only going to be a very brief summary of roles of glaciers, and I will present some recent data, mostly which did not involve scaling, but shows you something about the glacier-climate relation. Then I will lead you through, very briefly and non-mathematically, through the stochastic scaling procedure. And finally, I will discuss at the end why this new procedure, this new tool, is so wonderful, and give you some results on ice, climate, and sea level change. I'm interspersing a number of scenic views in here just as placeholders to tell you that now we come to a section of the report. Glaciers in the Earth system. To make this talk a little shorter, I'm not going to talk about many geophysical and hydrological implications. I will talk a bit more about climate and climate change, and then point out the problems that we have trying to make a global synthesis with existing data. As you probably know, glaciers exist in all continents except Australia, at all latitudes, including the equator, and in all kinds of sizes, from Massachusetts-sized glaciers down to little tiny piddling things. I won't mention very much about the geophysical aspects, simply to say that there are some very interesting solid earth implications of changing glaciers. As glaciers lose mass, they unburden the crust of the mantle, and the mantle responds, and this can be detected and used to infer properties of the mantle and the crust to considerable depths on a regional or global basis. Just briefly about hydrology, glacier runoff is rather different from ordinary precipitation-caused runoff. It responds in sort of an inverse way to precipitation, so that, as Andrew Fountain has pointed out, the coefficient of variation of glacier runoff, that is, runoff from basins that includes perhaps a fourth or a third glacier cover, that coefficient of variation dips way down because the glacier runoff is counterbalancing the peaks in ordinary precipitation. This is also very true on a long-term basis, in that at the present time, with global warming and ice wastage, a lot of water is coming out of ice storage, so that the, quote, normal runoff of many large streams like the Susitna in Alaska, the Columbia River in the Northwest, and elsewhere, is augmented by this release of glacier water. That, of course, cannot always continue. This is an old diagram modified by Andrew Fountain, which sort of shows the basics of Glaciology 101. This is the flow diagram whereby snow and ice generated in the atmosphere by the meteorological environment can be seen as surface mass and energy balances at any point on the glacier. The difference between that input and output is what we call the net mass balance, and that is the critical role in terms of looking at glaciers and climate. This can be defined at a point or an average over a glacier, which is B dot bar, or just the winter balance, which is a measure of snow accumulation, or the summer balance, a measure of melting. And the dimensions of balance are normally given in meters of water equivalent per year. The net mass balance then in general causes stream flow, causes a change in thickness and a response of the glacier, change in the geometry of the glacier, and so on, and there are a lot of feedbacks involved. This is a compilation of existing data extended by some good hydrometeorological modeling. I apologize that a couple of glaciers didn't show up very well on this slide. In fact, they don't show up at all. But this line is the John Quat Glacier in the Caucasus, the Storebrain in Norway, the Greece glaciers right in here in Switzerland, the Kozelski Glacier is in Kamchatka, the Abramov is in the Pamirs, Tian, yeah, I think. And the South Cascade Glacier in Washington State is a line that goes way down here. This is the cumulative mass balance as measured and modeled, and it shows that these glaciers are in fact wasting away and that water is going into sea level rise. Here's a graph that my colleague Mark Diergeroff provided from existing data, making a straight arithmetic regionally weighted average of glacier mass balances, and you see in terms of sea level equivalent, the glaciers are wasting, causing sea level to go up. The climate is bouncing around a lot more, but in general, the climate is warming, as we know. This is a plot of the winter balance. It's a measure, again, of glaciers all over the world, averaged and regionally weighted. The winter balance is a measure of the snow accumulation. And you can see through time that it's increasing very slightly. Down here is the standard deviation of winter balance, and it's increasing quite markedly. This is the summer balance, the amount of melting on the glaciers, and it's increasing markedly, and its standard deviation is increasing slightly. What this means is that the snow accumulation on the glaciers of the world in the last few decades has been increasing slightly, but that's more than counterbalanced by the increase in glacier melt. Therefore, the glaciers are in fact wasting, and what's interesting is that the standard deviation, the variability of these parameters is increasing too. One might surmise that the climate is becoming more variable, if one didn't know better. Now we have a major problem with the statistical distribution of glaciers in the world. The fraction of all the glaciers with long-term mass balance observations, it's only 22, half of them are in Europe. But the fraction of glacier area in Europe is a piddling 1% of the total. And the amount of runoff contribution to sea level is only 1.6%. In other words, most of the world is totally unrepresented. And that's the reason why we need to have a technique to extend the results to a more proper global basis. And that's why we're so excited about the scaling technique. This is a a way that is used both to reconstruct the glacier changes of the last century and to project them for the future. This is a simple method that's been used. IPCC used it. Here is the volume of glacier I as a function of time. This is the volume of glacier I minus some V sub O, some calibration volume. This is the sensitivity of glacier I to changes in temperature. That is, T of T is a temperature scenario, like you might get from IPC, and that's divided by the response time. It's actually a lot more complicated than that. The sensitivity should also be considered a function of precipitation. So in order to understand the contribution of glaciers to sea level, for instance, during the last century or in the next century, all you have to do is to sum over I. Unfortunately, I is more than 100,000. And oops, I'm sorry, I leaned on the wrong button here. Because there are so many glaciers, and all of these properties, of course, are distinctive to an individual glacier, we have to make very unrealistic assumptions in order to come to an average. A lot of people have tried to make this average for the last century, including myself. I'm not listing the authors here, just the date of publication to protect the guilty. But as you can see, these estimates in terms of millimeters per year of sea level change vary quite a bit. They all have huge error limits. You really shouldn't trust any of them too far because there has not been a good scaling procedure used to fill in the enormous blanks in the data. Another scenic, this is supplied to me by Mark Diergeroff, about 5,000 meters high in the Tian Shan. So let's now turn to the scaling technology. I'm going to talk first a little bit about self-similarity and the kinds of glaciological variables that we can deal with. Then I'm going to talk about distributions of glacier data. And then I will talk about the stochastic scaling algorithm as we have it. And then some data which tests theory with observation and gives some interesting results. Let's look at the kinds of data that we need to get from glaciers. Some of these data are very easy to get, like area. You can get that off a map or off a satellite image or whatever. Air photos, very, very simple. You can get a lot of data on glacier areas very quickly and very cheaply. Slope and elevations and changes in surface elevation are not quite so easy, although with some of the new results in laser and radar altimetry, getting change in surface elevation isn't too difficult. Some things are labor intensive, like mass balance. I think I remarked in an earlier lecture that the most important technological advance in glaciological instrumentation was Right in the Rain graph paper. Probably the second greatest technological advance is the aluminum grain scoop, because we glaciologists spend an awful lot of our time shoveling snow to measure mass balance. Velocity in the conventional way is tough, but with modern radar, it's possible, interferometry, it's possible to get velocity pretty easily. To get thickness and volume, we've got to do radio echo sounding, which is tough, and to deduce the response time of a glacier, a real glacier, is extremely difficult. So wouldn't it be nice if we could take some of these easy, where is this pointed there, some of these easy characteristics and derive from them the more difficult ones, like response time, volume, and so on. This slide didn't come out very well. It's from a paper by Barr and Peckham, in which the area between two contour lines of glaciers in the Chugach Mountains has been colored either black or white. And if you squint at this, or especially look at the original publication, you can guess that there is some self-similarity involved in here. I cut a little piece out of that, an overhead, and project it now as an enlarged version. And again, it looks like there might be some self-similarity. And in fact, you can prove rigorously that there is, as Barr and Peckham have. Now, I did not use the F word, fat or otherwise, but it may be appropriate. So what you need to start with in stochastic scaling is a distribution of something. And it's nice to me have that something be something that's easy to measure, like size, area, or in this case, the square root of area. And here, for one well-inventoried region, I plot the number of glaciers which are equal to or greater than a certain size as measured on the horizontal axis. Now, if you take the vertical axis, the number of glaciers, and divide by the total number, then you essentially have the cumulative probability function going from 0 to 1 that a glacier is equal to or bigger than a given size. That's the starting point. Now I'd like to run through very briefly a roadmap of the stochastic scaling paradigm developed largely by Dave Barr. And if you're interested in this anymore, you could look at Water Resources Research or Journal of Geophysical Research in this past year. The self-similarity that we saw implies that there are power law relationships between the variables. What you first do is express the pertinent physics. For instance, for ice flow, the conservation of mass and momentum, and a constitutive law for ice. This is not a Mickey Mouse statistical generalization. It, in fact, involves the true physics that make glaciers work. Secondly, you define characteristic values for each variable. For instance, the variable thickness, you might consider the characteristic value to be the mean thickness. Doesn't matter how you do it, you just have to stick with it consistently. Then we relate these in a power law sense, develop closure conditions, so instead of having proportional to, we can say that this is equal to k times such and such. And that then gives us the ability to relate the distribution of any one variable to the distribution of any other variable. And I use here volume and area because they're the simplest to understand, but you can relate width to length, steepness to speed, anything you want. Here's a cartoon that expresses the same thing. We start with the cumulative distribution function in which the probability of a area, S, is equal to or greater than a designated area, S, plotted on the horizontal axis. That goes into a power law equation, which results then in a distribution of volume, a cumulative probability distribution. Volume is hard to get. S, area, is very easy to get, so we've suddenly leapfrogged to get a distribution of a variable which is very difficult to measure. Here's a comparison of theory and observation. This is all of the mountain or valley glaciers that I could find in the world in which there were some pretty good measurements of thickness and therefore volume. It's about 150, and they're all over the world. Many of them are in Central Asia. And you see it on log paper. It looks like a pretty good power law distribution. And in fact, the slope, the exponent, is 1.33, whereas theory says it should be 1.37. There's about a 3% difference, which I can explain, but not quickly. If we look at ice caps, they have a totally different mass balance distribution, and therefore the predicted slope is 1.25, and in fact the observations show a slope of 1.25. Here is the toughest parameter or variable to measure, response time. The conventional theory, which is attributed to Thomas Johannesson, says that the response time is probably best given by the mean thickness divided by the mass balance at the terminus. You can also use this formula, and Thomas showed that these were in fact identical. But to measure either of these is not a simple job. It requires a lot of measurements on the glacier surface itself, which are not trivial at all. Therefore, calculating response time is a tough exercise. But if we use scaling, we find that the response time is proportional to a factor, C sub m here, which is the mass balance index. It's the gradient of the mass balance with length measured at the equilibrium line for you glaciologists, raised to a power n, and then the area raised to a different power m. I apologize for these exponents. Those two m's are not the same, but I did this rather hurriedly. So this says that if we knew the mass balance index, that power n, the surface area, and this power m, then we could calculate tau. Now, the problem here is that C sub m is a mass balance index, and it requires measurements on a glacier to make, or if you have this measured in an area of many glaciers, it may be possible to assume that the various glaciers in the area have similar values of C sub m, and therefore you can estimate that. N and m, the exponents are well known, and S, of course, is the area. So lo and behold, we can get a response time much more simply than the conventional. Okay. I hope that my quick roadmap through the stochastic scaling procedure is clear. Let's move on. This scenic from Wyoming says that we're leading to the last section, the summary. I first of all want to say why the new methodology is useful, because of it gives us a better strategy for data collection. It points out that glaciologists and river basin hydrologists ought to be talking together more often, because there are great similarities in analysis, and it's a powerful methodology for using abundant, easy data to estimate more difficult variables and relations. Those that are designing mass balance and other similar regional assessments can use this methodology now to modify for greater efficiency their data collection strategy. First of all, the stochastic scaling business says you should concentrate on simple but meaningful measurements to obtain a large database. Of course, you also have to include some intensive studies for calibration. These are largely going on now. But the main idea is to get more and more simple measurements to use as a base for scaling distributions. Secondly, very important, we need to measure a random collection of glaciers of all sizes. Traditionally, people have said, oh my, we've got to find the representative glacier. I've always wondered what that meant. So they find a glacier that is accessible and about the right size so they can walk it in a day and so on. And what's really important is that you include a suite of glaciers of all sizes. And let me illustrate that. This is a little study that David Barr made. The Alps has over 5,000 glaciers, all very well measured. And here is the area distribution function, the cumulative area probability function for all of the glaciers of the Alps, where it says all data. Now, David Barr just said, okay, out of that 5,000, we'll just pick the 1,000 smallest ones. And we got this curve, which is obviously wrong. And then he said, we'll just pick 1,000 glaciers out of the middle, which is sort of what people do now. And that's wrong. So he said, well, we'll just pick 1,000 glaciers at the large end of the spectrum. And that gives this, and that's not a very good representation either. And then he said, let's select randomly 1,000 glaciers of all sizes, and we get that. Then he says, let's select randomly a different set of 1,000 glaciers, and we get that. And then he does it a third time, another random set of 1,000 glaciers, and all of them give a curve which is virtually identical to that of all data put together. So it's very important not to ignore the big glaciers or the very small ones. Finally, if we know that there are ways of scaling that will allow us to make better analyses and syntheses, we should take these into consideration in developing our measurement programs. Well, that scenic, which happens to be a fire and ice scenario out of Mount Baker, says that we can go forward to the last point, a summary on ice, climate, and sea level, in which we can actually use some of the scaling techniques. It's not complete, but we are getting there. We'll look at distribution of glacier sizes, changing glaciers and changing climate, and what's happening this past century and what is likely to happen in the next century. Here's a graph that I published a year or so ago that Sam Kovac published in a special report of Krell, honoring somebody. And it gives you the total area of the glaciers of the world as a function of their size class over many orders of magnitude. The state of Massachusetts falls in here if it were a glacier. And it's also broken down by polar, subpolar, temperate, maritime, and temperate continental, and tropical. This kind of analysis would never have been possible had we not been able to use scaling. This also is something that was published. It's an estimate of glaciers of different types, ice caps and valley or mountain glaciers, their numbers, their areas, their volumes, and the sea level equivalent. Again, this kind of a compilation would never have been possible, at least as accurately, without the use of scaling. So, I'd like to illustrate some of the changes in mid-latitude glaciers, which is where most of them are that are being measured. Switzerland glaciers are decreasing. If you look at the second line, the area of glaciers of the Alps, including Austria, Italy, France, Germany, and Switzerland, have shown about a 35% decrease in area and about a 50% decrease in volume. In other words, half the ice of the Alps is now gone with respect to the late 19th century. New Zealand, big changes. Caucasus Mountains, again, half the ice is gone. That number was obtained by scaling, looking at the power law relation between volume and area. And in the Tian Shan, 22% gone in just the last 40 years. Here's one of America's favorite glaciers. If you look between the heads of the tourists in the background, you can see some ice. It's called Grinnell Glacier in Glacier National Park. And this past summer, Al Gore jogged up there and gave a pronouncement on global warming. In fact, you look at this and you see a moraine way up there. And the glacier border is now down there. You can tell that it has decreased a lot. In fact, I've made a number of back-of-the-envelope compilations which show, at least to my satisfaction, that in 50 to 70 years at the uppermost, this glacier and all the other glaciers in Glacier National Park will be gone. If you want to see glaciers in Glacier Park, you'd better hurry. Now let's look at Arctic glaciers. A different picture. Very slight changes in area, in one case, nothing at all, and very slight, comparatively, changes in volume over 100 years. So there are regional differences. Let's go to Africa and places like that. The snows of Kilimanjaro are fast disappearing. 73% of the area is gone already. Mount Kenya, the Lewis Glacier, the biggest glacier in Africa, it's 92% gone in the last century. And I thought that last statistic was kind of interesting. In 1980, the Spaniards counted 27 glaciers. In 1994, just 14 years later, the number had dropped by half. So things are happening. To sum up, in the last century, glaciers have contributed about 20% to sea level rise. This contribution is currently increasing, mainly because of increasing summer ablation. And the year-to-year variability of glacier mass balance seems to be increasing. Glacier changes show very strong regional differences. Arctic ice caps and glaciers show very little change. Mid-latitude glaciers, rapid wastage, small continental glaciers, many are disappearing. And glacier reservoir depletion is causing significant increases in the flow of some rivers. That, of course, will be gone when the glaciers have disappeared, that increment. Now the $64 question. What's going to happen in the future, especially in regard to sea level? Oh, I forgot. This is the spring meeting, isn't it? I'm sorry. Is that better? Actually, that's a scary slide that has very little reality to it until such things as the West Antarctic ice sheet disappear. But to the year 2100, the IPCC estimates are only a fraction of a meter rise in sea level due to small glacier retreat. This is the IPCC graph showing the different components of sea level rise. This is a consensus as of 1994 and 95. It would be a little different now, but not greatly. And as you can see, thermal expansion is now listed as probably the greatest contribution. Glaciers and ice caps, next biggest, and then Greenland and Antarctica, which are very much unknown. Now, an accurate projection of future sea level rise may be possible if we can define probability density functions on a regional basis for easily measured characteristics, such as area. And then if we can infer the more difficult characteristics, such as response times, by using stochastic scaling, and if we can get good data on mass balance controls from mountain areas. And I just have to sadly show you this slide. The largest glacier in Asia, it's 77 kilometers long. It's been well studied for decades by the Germans and the Kazakhs and the Russians. And there's a meteorological station at over 4,000 meters in altitude with 60 years of record, just what we need. All closed down for economic reasons. Fedchenko Glacier in the Pamirs. We really need those data, and it's a shame we can't get an international consortium together to resuscitate such a unique and interesting station. Well, there's another scenic slide. It says that something new is coming up, and in fact, I will close with some acknowledgments. First of all, David Barr, who is principally responsible for the scaling algorithm and its application for glaciological work. Mark Diergeroff, another one of my colleagues, for careful analysis of global mass balances and other data. Many contributors of published and unpublished data and co-workers like Tad Pfeffer in our office that have made this sort of a compilation possible. I'm gratified I'm grateful for the AGU for honoring me with this opportunity, and Walter Langbein, who helped get me started in the right direction on a fun and productive career. And I will close just by saying that glaciology is a neat field. It's intellectually challenging, it's very interdisciplinary, and it takes us into areas of great scenic, aesthetic beauty. I recommend it to anyone. I'm really very, very happy that I got into this field some years ago and pursued it ever since. Thank you very much. Good.
And I'd ask you to speak up loudly and distinctly when you ask your question. Do you have any?
Yes.
What is this final slide?
Oh, it's a painting by some amateur of the Blue Glacier in the Olympic Mountains.
Who is the amateur?
Oh, some guy. Yes, but, oh, there's one.
Are people giving much thought to the possibility of a change in climate back towards more of a cooling trend and perhaps glacial growth? I mean, if things are warming, is there something that might trigger a reverse?
Well, the physics of greenhouse gases says that they will cause a warming as long as they are in our atmosphere, and carbon dioxide and gases like that are not scrubbed out of the atmosphere for a long time, and mankind is continuing to inject them, and therefore most of us that have been involved in the IPCC, the Intergovernmental Panel on Climate Change, are pretty convinced that it's going to keep warming for centuries, no matter what the climate is trying to do in the background.
I was curious,
Yeah.
Mark. You told us a little bit about the European glaciers, and I got the impression they're very well studied. I wonder if you could give us some insight into the North American glaciers and how well they're characterized.
The first scenic that I showed was South Cascade Glacier, which is a program that you mentioned that I set up as part of the Water Resources Division office in 1957 or so. That is the one glacier that has the longest record, and it has a very complete record. Beyond that, the Blue Glacier in the Olympics, the last painting, has a long record, but it's from the mass balance point of view, it's incomplete in that the winter accumulation has not been measured. Now, there's a problem there because it can exceed 10 meters of water equivalent. That's hard to measure. It has good dynamics. Other glaciers during the International Hydrological Decade that we started included the Little McClure Glacier in the Sierra, which lasted only a few years, the measurement program. The Gulkana and Wolverine glaciers in Alaska. Those measurements more or less continue. And then the Canadians have got a suite of glaciers that they began in the middle 60s, both in the Rockies and in the coastal ranges. So there are a few glaciers in North America that are being measured, but nothing is as important as those in the Alps or in Norway and Sweden. The longest mass balance records come from Scandinavia. Sarush?
Point has the debate about the ratification of the Kyoto Treaty. Discussed, and even, in fact, AGU is working on a position statement on global warming, and the split between the scientific community and others, whether any of the warming is to be attributed to the greenhouse gases. Evidence like this, you think, does suggest for the treaty, is there anything that people, at least as far as glaciologists are concerned, that would attribute to the CO2 emission and the greenhouse gas emission?
I have to choose my, do I need to repeat the question? Yeah. Briefly, Sarush is asking, from the glaciological point of view, can we see evidence that greenhouse gases are causing this warming? Because I have to choose my words very carefully here. We see warming. There's no doubt about it. We see increasing glacier melt. No doubt about that. We can't tell what's making the glaciers melt. There's very little argument in the scientific community. I sat on the IPCC as a lead author, and there we had literally hundreds and hundreds of the best experts we could find arrived at a consensus that says that you can just now see patterns which suggest or indicate strongly that there is discernible human impact on the climate in addition to ordinary climate variability. Now, there are people that don't like to hear these statements, and therefore there is a big press push to try to countervail them. All I can say is our consensus was arrived at over a period of about 2 years with literally hundreds of people contributing. And my chapter, for instance, I think had 380 peer reviews, including from industry. So it was hard fought, and if you want to come out with some different conclusion, you really ought to start out with that broad consensus. There's somebody there.
Yes, Eric.
We hear about all the coring in Antarctica and Greenland. How much coring has there been done in the mountain glaciers? And there hasn't been very much. Is there any potential for getting historical data that would be important to understand those glaciers?
Yeah, the question is there ice coring going on in the mountain glaciers, and is there a potential here? And the answer is yes on both counts. The problem is that glaciers like South Cascade in Washington State are so warm, that is, there is water coursing through them all the time, that it's very difficult to get much of a climate signal. Furthermore, the accumulation rates are so huge that 1 year produces, an enormous amount of ice, so you can't go back in time. However, if you go to a very high altitude, as Lonnie Thompson has done, in the Andes and in Central Asia, up to 5,000 and 6,000 meters above sea level, where it's cold, there are ice caps that trap a nice climate record that can be recovered through ice coring, and I think some of that is very, very exciting. Very good records. But he points out that he has seen, just in the few years that he has been working, that the ice cores, the ice caps, are warming. And some of these records are deteriorating before our very eyes. But yes, high altitude ice caps are very productive of climate history.
Yes.
Do you have any sense what proportion of the loss of the mid-latitude small glaciers is due to a change in precipitation type, that is rain versus snow, as opposed to absolute warming?
The question is for the mid-latitude glaciers, is this wastage due to just warming, or is it due to a change in the form of the precipitation or something like that? And I can't really answer that. It is true that a little warming may raise the freezing level to the point of where you have more rain and less snow. And, this could be a cause, but we we can't separate those variables very well. Yes.
What are the relative impacts that you see on rivers? I hadn't really thought about that. But sea level rise is one thing we can all imagine, but what impact do you see in the reduced flow of rivers?
The question is, what impacts do we see on the flow of rivers? Global warming is causing glaciers to thin, lose volume. That ice goes into the rivers as flow, water flow, and in some rivers it's appreciable, that extra increment, just due to the wastage of glaciers. It's been calculated, for instance, in the Susitna Basin of Alaska, which is big, had some major hydropower installations planned, that 10% of the annual flow was due to water coming out of storage. Now, what's interesting about that is that either the climate can change, I don't think that's going to happen, or the glaciers can disappear, and in that case, that increment, that extra increment, disappears. Does that answer your question?
Greenhouse gas emissions.
Could you repeat that, please?
I wonder how much is known about variations in solar output versus greenhouse gases with regard to global warming.
The question, of course, is a good one that has been argued in the literature. It's not my field, so I cannot really comment very intelligently on that. But yes, there is a solar influence on the climate. But I can't say how much.